Welcome back, everybody. This is going to be the first of two videos about chords in circles. There are several theorems that we're going to need to prove and then figure out how to use. But just to begin with, let's start with some vocabulary. Chord is just a segment, but it happens to be a segment where both of the endpoints lie on the circle. We don't have any special symbol for chords because they're just segments, so we notate them in exactly the same way. Segment AB is chord AB. There are, of course, an infinite number of chords that we could draw in any circle, including circle C here, but one type of chord is incredibly important. Chord DE, as I'm sure you're already aware, is a diameter of this circle. And we can define diameter in a lot of different ways. We can say that it's the longest possible chord in a circle. We can say that it is the sum of two collinear radii. But the definition that we usually stick with, it's just a chord containing the center of the circle. But here's another important point. Diameter DE actually also creates a central angle, DCE. And as will be the case with every diameter, the measure of that central angle will be 180 degrees. In an earlier video, I asked the question, what's the one type of central angle that does not divide a circle into a major and a minor arc? Well, we found it, any diameter. Since its central angle measures 180 degrees, it divides the circle into two congruent arcs. Each of those arcs measure 180 degrees. So it divides the circle into semicircles. Another way to say this is that it intercepts two semicircles. Remember this vocabulary word again. Central angles, and in fact chords as well, intercept arcs. In the case of a diameter, the arcs that are intercepted are both semicircles. And in fact that gives us a little more information about plain old chord AB as well, because there's a central angle that's associated with chord AB. We can create angle ACB, and that central angle will intercept the same arc, AB, as chord AB does. So just looking at the picture, we can see that chord AB, arc AB, and angle ACB are all closely related to each other. We know that the measure of arc AB is going to be the same as the measure of angle ACB. And to get back into the fancy language, we say that arc AB subtends both chord AB and angle AC. Just to point out that word subtends one more time. Since chord AB, arc AB, and angle ACB are also closely related, and the angle and the chord both define that arc, we can say that in all cases other than a diameter like DE, a chord, just like a central angle, will divide a circle into a minor arc and a major arc. In this case, chord AB creates minor arc AB, but it also creates major arc BDEA, since that larger arc also runs through point D and point E before it gets back to point A. Now this particular naming of this major arc isn't absolutely necessary. We could probably shorten it into, if we wanted to, and we would have no confusion. The arc that begins at B, runs through D, and goes all the way through A, also has to pass through point E. So it's not entirely necessary to include E in the name of the arc, but you certainly can if you want to. We're going to take a look at three different theorems having to do with chords in circles. Let me draw them out and write out what the theorems say symbolically. The first theorem looks something like this. Let's say we have a setup like this. Circle P and two chords, A, B, and C, D. This first theorem says, for any circle, two chords will be congruent if and only if the arcs that they intercept are also congruent. Well, we can just add that to the diagram. Remember, this if and only if is incredibly important. It means that the statement has to work in both directions. If I'm told at first that the arcs are congruent, then I know that the chords are also congruent. If, on the other hand, I'm told that the chords are congruent, then I know that the arcs are also congruent. We won't prove this outright, but consider this in trying to prove that if we know the chords are congruent, we also know the arcs are congruent. If we begin with the diagram as it is now, then we can create two triangles pretty easily. And the great thing about these two triangles is that the segments that I've added to create the triangles are all radii. As a result, AP, PD, PC, and PB are all congruent segments. Now we're basically all the way to proving these two triangles congruent to each other. And since we know that central angles and arcs are so closely related, in fact, we measure them the same way, we should be able to say something about arcs AB and DC. Let's take a look at the second theorem and talk our way through a proof. Here's how we set up this theorem. Let's say we have a circle, Q in this case, with a diameter, PR. Now we're going to add something else. We've added in chord ST. Let's mark the point on the diameter where ST intersects it. We'll call it point H. Given that we have this diameter, PR, in circle Q, this theorem then tells us, with that diameter, if the diameter and the chord are perpendicular, then the diameter bisects the chord. But also, because of this if and only if, we can say it in the other direction as well. If we happen to know that the diameter bisects the chord, we also know that the chord and the diameter must be perpendicular. Well, let's prove this in one direction. Let's start with the fact that these are perpendicular and prove that the chord ST is bisected. So this setup is now what we're left with. Just the idea that angle SHR, and of course the three other angles around point H, are right angles. Without getting too formal about it, let's just talk our way through how we would figure out if SH and HT are congruent. Well, if you're at all like me, you see triangles everywhere. So let's put in a couple of triangles here and see if we can find congruence. It's always a great idea to draw in triangles where sides are radii, because we know that all radii in a circle are congruent. So we can add QS and we can add QT, and we know right at the top that these are congruent segments because they're both radii. Now this tells us a few things. We can say that triangle TQS is isosceles, and so angles T and S have to be congruent. Or we can look at this as two separate triangles, say triangle QHT and triangle QHS. It would really be helpful for us to know that these two triangles are congruent, because CPCTC, corresponding parts of congruent triangles are congruent, would then tell us that corresponding parts HT and HS have to be congruent. So let's aim for that. There are a couple of ways to do it. Perhaps we can start with the idea that the larger triangle QTS is isosceles. If that's the case, the base angles theorem tells us that angles T and S have to be congruent. The other thing that we know, just by the definition of perpendicular segments, is that the angles THQ and SHQ are both right angles. Great, so we're dealing with two right triangles here. In fact, right now, we already have enough information to say, by what theorem? Hypotenuse angle congruence. Since we're dealing with a right triangle, if we know that the hypotenuses are congruent, and we know that one of the remaining two acute angles are congruent, we can say that these are absolutely congruent. Another way to do this, and maybe one you're a little bit more familiar with, is to recognize that QH is congruent to itself. That's just the reflexive property. If we know that, then even if we don't recognize that angles T and S have to be congruent to each other, we can come to this same statement by hypotenuse leg congruence, knowing that the hypotenuses QS and QT are congruent, and QH being in both triangles is congruent to itself. This then allows us to reach our final conclusion that segments HT and HS are congruent to each other, just by CPCTC. And this was one of our statements that needed proving. We could go on one more step to say that PR bisects ST just by the definition of segment bisector, but I think we've gone far enough here. Proving this in the other direction, beginning with the idea that chord ST is bisected by the diameter PR, and then going back to prove that these must be right triangles, is an incredibly similar proof, because we have to prove the triangle's congruent again, and use CPCTC, but this time to prove that angles QHT and QHS are congruent angles. That way, knowing they're congruent and a linear pair, they must be right angles. But let's take a look at the last theorem. This last theorem actually relates back to the first theorem, but it's set up like this. Just as in the first theorem, we draw a circle, circle C in this case, and two chords, A, B, and D, E. But in this case, we're not concerned about congruent arcs. What we're actually concerned about is the distance from point C to each of these chords. Now, remembering that we always measure distance along a perpendicular segment, we can talk about CF as being the distance from point C to chord AB, and we can talk about CG as being the distance from point C to chord DE. And this is where this theorem gets interesting, because it says AB is congruent to DE if and only if CF is congruent to CG. So remember, here we're talking about chords themselves being congruent and the distance from the center of each of these chords being equal, which is to say that the two segments which are perpendicular to the chords must be congruent. Once again, if and only if shows up here, so we can say that if we know the chords are congruent, then we know they're the same distance from C, and if we know that the chords are the same distance from C, then we know they must be congruent. Let's walk through a proof in this direction. I'll shorten this up a little bit. Obviously, knowing that the measures of AB and DE are the same leads us directly to knowing that they're congruent. So the information that we're given here tells us that CG and CF have to be congruent, since their measures are equal. Now, as we always love to do with these kinds of proofs, let's add some radii. Great. With these radii added, we already know that they're congruent to each other, all four of them. Let's also, just for a reminder, sketch in that we know of two other right angles as well. Now it comes down to proving the congruence of four triangles, and it's not too bad. The statement that we can almost directly make is that all four of these right triangles are congruent to each other, and we can say that must be the case by hypotenuse leg congruence. Since GC and FC are in each pair of triangles, and all of the hypotenuses have the same length, and we already showed that GC and FC are congruent, we have hypotenuse leg right away. Well, from that, CPCTC tells us that all of these segments that make up the two chords are congruent. We're almost there with this proof now. The last thing we actually need to use, the segment addition postulate. In this case, knowing that and we can do a substitution. And we have some choices we can make in that substitution. Maybe we can substitute these two and substitute these two, and we can actually show that DG plus GE is also equal to AB. Knowing this information allows us to show that the two chords are congruent. I'm going to leave the formal proofs to you, but I wanted to walk you through how some of these proofs would look, since all of this comes down to proving congruent triangles. In the next video, we're going to put these theorems to use in solving some algebraic problems. Thank you, everybody.